All right, so let's take a look at the second part of section 9.2. Okay, remember that when you graph a point in polar, it doesn't use xy, it uses r theta. So what we're going to do today is we're actually going to get into not just graphing single points. We're going to graph like an entire equation in polar. All right, so let's look at this one. In polar, usually when you write a graph, like in function, we write y equals. In parametric, we do x equals y equals. In polar, it's r equals. Okay. On your calculator, if you go to mode and you go to polar, it'll show you exactly what you see right there, r equals. So remember, r stands for what? Radius. So when they ask you to graph r equals 2, they want you to graph every single point, because it's a picture, every single point that's 2 units from the origin. What would that look like if you graphed every single point that was exactly 2 units from the origin in every direction? Yeah?
It would be a circle.
Yeah, it'd be a circle. So here's 2 units away. That's 2 units, 2 units, 2 units. All these points are 2 units away. So the graph of r equals 2 is a circle. All right. Anytime you do r equals, it's a circle. Remember, if you just do r equals 2 and you do a standard zoom, it's going to look like an ellipse. If you look carefully, it is 2 units in each direction, if you look at the tick marks. But it's because the screen is rectangular. So if you really want to see it proportionally, just do zoom square. And what that does is it adjusts the window so that things don't look distorted. Okay? All right, so that's the graph of r equals 2. Let's look at this one. You can't graph this on the calculator. Right? So just like if I gave you the equation like this, x equals 2, that's a vertical line at 2. You can't draw vertical lines on the calculator. Well, you can't, that's in function mode. When you're in polar mode, you can't graph theta equals a number. The way to graph it is by hand. So what does theta stand for? Yeah? It's an angle. All right? What angle is it? Well, if you converted it to degrees, that's like, let's see, 2 times 180 divided by pi. It's about 115 degrees. Okay, so you can keep that in the back of your mind. It's about 115. So what they want you to do this time is graph every single point that has an angle of 115 degrees. The radius can be anything. So you could graph 2, 115, 4, 115. You could also graph -3, 115. Graph every single point you can think of that has an angle of 115. Right, so let's start to do that and see what it looks like. So 115 degrees is just a little bit after 90, maybe a little bit more, but that's okay. If we did 4, 115 degrees, be right about there. If you did 3, 115 degrees, it would be there. 1, 115 degrees, it would be there. What is this kind of looking like? It's a line. But now watch what happens when you do the negatives. -3, 1, 2, 3, and now go 115 degrees. You end up right about there. -1, 115 degrees. So what you're getting now, does that look straight? Kind of. What you're getting now is the part of the line that goes in quadrant 4. Right? So whenever you have theta, it's not bad. Whenever you have theta equals a number, you basically get a line. It's supposed to go right through the origin, but mine's a little bit off. Any question on that? Now, you can do arbitrary lines like with a certain slope and a certain intercept. It's a little more complicated in polar, so we're not going to talk about that right now. But that's the only kind of line you would need to know. Any questions on the first two? All right. Great. So now we're going to look at a special kind of graph that we do a lot in polar. And it's a little hard to just kind of sketch the whole thing at once. Like the last two were easy. Circle, line, weren't too hard. We're going to kind of look at this graph in sections. There's like 4 sections to it. So we're going to make a table, and I think the table will kind of help us. Okay, I want to graph that. 3 plus 3 sine theta. Now that's a common pattern. A number plus the number times theta. There's a name for that. Okay, I'll tell you what the name is after. Or if I do a good job drawing it, you might be able to see what it looks like, and then the name will make sense. First thing is, just like you have in parametric, when you graph in polar, this is like your interval. Right? So remember you had a T-min and a T-max when you did parametric? Well, now you've got a theta-min and a theta-max. It's the same exact thing. You're basically saying, okay, here's the values you can use for theta. Here's the smallest, here's the biggest. Right? Theta step, just like T-step. If you make your T-step too big, your graph is going to look kind of jagged. If you make it way too small, it's going to take forever to draw. So try to find a good balance where the graph looks, smooth the way it should, but it doesn't take like 60 seconds to draw the thing. Okay. All right, so first thing I want to think about is the lowest and highest value you're ever going to get for the radius. So what that means is I'm going to figure out what's the farthest I ever am from the origin and what's the closest that I get to it. Okay, to do that, we need to look at this function. That's the only thing there that can change. The 3 in the front doesn't change. The 3 right next to the sine doesn't change. So let's just think about sine. Okay, here's your graph of sine. What's the highest value that sine can ever hit? Yeah, 1. Now what if you triple that? 3. And what if you add 3 more to it? 6. So the largest or the furthest you could ever be from the origin would be 6 units. Right? Now let's see the smallest, or the closest we could be. What's the lowest that sine ever hits? -1. And then times it by 3? +3. 0. So when we draw this, you can see this is not going to be a circle. The radius is going to change. What's it going to change between? It's going to go between 0 and 6. So at some points it'll be bigger, some points it'll be smaller. Any question on that? But I will tell you, the shape is going to connect. It's going to connect to itself. So it's not like a spiral that doesn't connect. This shape does connect back to itself. So it makes a closed shape. That's the same graph I just put up. All right. So what we're going to do is we're going to kind of look at this problem over 4 different sections. First, the section where it's increasing. Then, the section where it's decreasing, but it still hasn't crossed the axis yet. Still decreasing till it hits its lowest. And I'll just leave the last section in black, where it starts to increase again. So the first section I'm going to look at is the red one. Here's the red one. From 0 to pi over 2. Look at the sine value. For that section in red, that's what I'm looking at. Where does the sine value start for the red section? 0. It starts at 0. So it goes, actually, I'll just use an arrow. It goes from 0 to, what's the highest value that you hit for sine in the red section? Just up to pi over 2. Yep, goes up to 1. So now let's figure out what's happening in the formula. We know what this is doing. It's starting at 0, and it's going to 1. Then we just have to take into account that arithmetic in front. So it's going to start at 0. What's 0 times 3? 0 plus 3. 3. So in this section, the radius is going to start at 3, and it's going to grow. What number is it going to grow to? Well, sine goes from 0, and it grows to 1. So if sine's biggest value is 1, 1 times 3 is 3, plus 3 is 6. So when we sketch it, and we're on our graph, as we go from 0 to 90, the radius is going to increase from 3 to 6. So it's almost like it's spiraling out. Okay? But it doesn't keep spiraling out forever, because 6 is the biggest. It actually starts to kind of come back in at one point. And let's look at the blue section. So the radius is growing from 3 to 6 in quadrant 1. It's spiraling kind of out. Now, blue section. This is quadrant 2. This is from 90 to 180. What happens? Let's look at the blue section. Where does the y value start for the section in blue? Yeah. Starts at 1. And where does the sine value go in the blue section? It ends up at 0. It ends up at 0. So this is just the reverse. It's almost like it's like a mirror image. It grew from 0 to 1. Now it's shrinking from 1 to 0. So the radius is going to do the same thing. It's going to start at 6 because the sine value starts at 1. 1 times 3 plus 3. Where is the radius going to end? Well, look at where sine ends. At the end of the blue section, the sine value is 0. 3 times 0 plus 3 is 3. So now the radius is shrinking back to 3 in quadrant 2. Okay, let's look at the green section. Okay, so the green section is what we're going to draw in the third quadrant when we make our sketch. What is the y value starting off at for sine in the green section? Rob?
The y value starting off.
Starting at 0. And what is it ending at when you get to 3 pi over 2? Negative 1. So let's see what's happening to the radius when we draw the quadrant 3 part. We're starting at 0. 3 times 0 is 3. Yeah, 3 times 0 is 0. Plus 3 is 3. But look where it's ending. Sine is going to go all the way to negative 1. What's 3 times negative 1? Plus 3? 0. So at this section, the radius is going to shrink all the way to 0. Where would your point be if your radius shrinks all the way to 0? It would be at the origin. So this graph is, when we draw it, it's going to go right through the origin. And now, the last part is the part in black. And that's pretty much a mirror image of the part in green. This is a symmetrical picture, okay, when we draw it. We're starting at a y value of negative 1, and we're heading up to 0. What's that going to do to my radius? Just the opposite of what happened in green. In the fourth quadrant, the radius is going to grow. So it's like it's spiraling back out from 0 to 3. Okay, so this is the column that's most important, the one on the right, because that tells us how far away from the origin to draw our points. All right, so let's see if we can make a sketch. All right, so I'm going to start. I could put circles on that if I wanted to. I'm not sure if that's just going to make it look. I don't think that looks confusing. Let's put the circles in. Well, this one. That's as good as I can do. All right. So let's label our angles. 0, 90, 180, 270. If you want to think of it in radians, pi over 2, pi, 3 pi over 2. Okay, so when we're at an angle of 0, my radius is 3. That's like graphing the point 3, 0. Radius is 3, angle 0. Now let's look at where it ends. When my radius is 6, that's the end of this section, I'm at pi over 2. That's the end. So 6 is the radius, pi over 2 is the angle. So I'm up here. And this is going to be connected. Now remember, the radius is growing the whole time in this section. So kind of think of it like this. It starts at 3, and as you start moving around, it gets a little bit longer. Okay, I'm going to erase these lines after. I'm just trying to kind of show you what's happening. But as you rotate, the radius gets longer and longer and longer until finally it gets to its longest. Okay, so the radius is growing as you rotate from 0 to 90. Any question on that? Yep, I'm gonna be scrolling up and down a lot. Yeah. So what's it gonna look like? It's gonna kind of look like that. That's what it'll look like. So you don't really need those lines. I was just trying to show you what's happening. So as you rotate from 0 to 90, the radius grows from 3 to 6. Now, it's a mirror image in the blue section. As you go from 90 to 180, the radius is going to shrink back to 3, from 6 to 3. All right, so basically, we just kind of mirror image this. Start at 6, and 3 is right here. Going to go like that. So now you can see as you rotate, it's getting longer and longer and longer until you finally reach 6. Okay. Any question on that part? All right, so now let's look at what happens in the third quadrant. That's between pi and 3 pi over 2. What's happening to my radius between pi and 3 pi over 2? Okay. Yeah, what's it shrink? From what to what? Yes, it shrinks from 3 to 0. So it starts at 3, and as you start to rotate towards 270, it kind of goes like this. It shrinks all the way to 0. So this part is going to kind of look like that. And the other part, as you rotate from 3 pi over 2 to 0, or 3 pi over 2 all the way back around to 360, it's growing again. From 3 pi over 2 to 2 pi, it's growing from 0 to 3. So it's like a mirror image of what I just drew in green. And that's pretty much what it looks like. Does that kind of look like anything? Yeah.
A heart.
Yeah, kind of. Not really. But it kind of looks like a heart. And that's why this shape is called a cardioid. Okay, so it kind of looks like a heart. I actually exaggerated it. It might look a little more bubbly, like a little squished. But that shape is called a cardioid. So let me type it in here. Now it's going to look similar. It's not going to look exact. 3 plus 3 sine theta. Right, and let's do zoom square. Doesn't look as much like a heart here, but kind of. So that's the shape that we just drew. Mine looks a little more stretched out, but that's okay. So that's called a cardioid. Yeah.
Can you back up for one quick second?
Wait there.
Yeah, you can do it. Time.
So if you change the numbers, like if you change the 3s to 2s or 4s, you can change the size of the cardioid. Okay? But the largest, as long as you keep it this way, like follow this pattern, the largest the radius can ever be is double the number in front. Okay? If you make these numbers different, like make one a 3 and one a 5, then you start getting weird things that happen. Like the cardioid can actually loop back on itself. So it might look something like this. So it's kind of like a heart shape, but then it loops on itself in the middle. we're not going to look at all the different things that can happen, but as long as you know that that shape is a cardioid. So cardioids can be one of two forms: a number plus or minus a number with sine, or a number plus or minus a number with cosine. We did the sine one. If you did cosine, it would turn the heart on its side. So it would look more like, let's see. You might get a cardioid shape that kind of looks like that. It's not as pointy as a heart, that's why I'm not trying to make it super pointy there, but it could turn it sideways, okay? Depending on if you use sine or cosine. Now, theta only has to go from 0 to 2 pi to get a complete graph. If you put in something less than that, like try 0 to pi, it's not going to work. You only got half the cardioid. You got quadrants 1 and 2. Okay. What happens if I did something like 4 pi? We did that with parametric. What would happen there? Yeah, if you go 0 to 4 pi, you might not be able to see it because it's small. No, I can't tell. But it did trace over itself. If I zoomed in, you could see it. Okay, so 0 to 2 pi, that's all you need. All right, so now we're going to look at how we can take an equation in polar. Actually, we're going to look at a cardioid, and we're going to change it to rectangular. Now, when we change it to rectangular, you're not going to be able to graph it, because there's going to be no way to get y by itself. We're going to end up with a relatively messy equation. Cardioids look nice and simple in polar. 2 plus 2 cosine. Nice and simple. They don't look that simple in rectangular. But the formulas that we can use to change between polar and rectangular, what you want to think of in your head is all your formulas that relate x and y to r. Here's one for x, one for y, Pythagorean theorem. We don't really use the inverse tangent one too much, but technically, I mean, you could, depending on what you're doing. We'll probably use the first three the most. Okay, so let's convert the cardioid we just drew into rectangular. So when I'm done, all I want to see is x's and y's. No r's, no thetas. And don't expect to get y alone. You're not going to be able to. You'll just have x's and y's everywhere. Let's start with this. When I have a trig function, when I'm trying to get to polar, usually the first thing I do is get rid of the trig function. Does anybody see a way that we could rewrite sine using something up above? Chris?
Sine theta equals y divided by r.
Exactly. So sine theta equals y divided by r. I still have r's, but at least I got rid of my theta, right? Sine theta isn't there anymore. We replaced it with y over r. Now, unfortunately, we got a fraction here. I don't really like to have fractions. So what could you multiply everything by to get rid of that fraction?
R.
Yeah, we can multiply everything by r. Now, what's in black and what's in red is really the same thing, as long as you put an equal sign there. But at least I don't have a fraction anymore. The 3y is fine. You can leave that alone. The r squared isn't. Is there anything I can replace r squared with to get rid of it and have just x's and y's? Yeah.
X squared plus y squared.
Yep. X squared plus y squared equals 3. Now we can't have that r there, but the 3y is fine. So if r squared equals x squared plus y squared, what would r be? Yep. You can't, I know what you did, but you can't you can't simplify it to that.
But if it's square root of x squared.
Yes, just the square root of x squared plus y squared. That is a cardioid if you write it in rectangular notation with x's and y's. I told you you wouldn't be able to get y by itself. Maybe you can't. And that's it. So to change from polar to rectangular, the goal is just to replace everything that's not an x or a y. So if you've got a sine or a cosine, deal with that first. And then if you have some r's, deal with that second. And that's pretty much how you do it. Okay, much more complicated looking in rectangular. Pretty simple looking in polar. I mean, simpler anyway. Questions on how? Yep.
How did you do the first part where you got r equals 3 plus 3y over r?
So we just rearranged and got sine by itself there. But if you divide each side by r,
Okay.
y over r equals sine. And that's what I put right here.
Okay.
So instead of sine times 3, y over r times 3. All right, so I'm going to show you two formulas that you can use to graph, take a polar equation and change it to parametric. So we just changed, what did we just do? We did polar to rectangular. Now we're doing polar to parametric. And then I think the very first day we did eliminating the parameter. So we've already done parametric to rectangular. That was a couple days ago. All right, so all you have to do is if you have a graph in polar and you want to change it to parametric, well, the first thing you have to remember is, wait, polar uses theta as the thing that changes. Parametric uses t. So the first thing is you've got to change all your thetas to t's. This is how you do that part. And then what you want to do is you've got to break it up. Parametric uses a separate equation for x and a separate equation for y. So how do you take this and pull out the x part and the y part separate? Well, it would be kind of like, let's say you had, I'll just do something simple. We'll do a circle. We already drew a circle in polar earlier. It's one of the simplest ones you can draw. Here's a single point. So forget about the whole circle. Just look at the single point. Well, if you make a triangle out of it, that's x, that's y, that's r, that's theta. If you want to know the horizontal part of your point, so you've got this point, you want to pull the horizontal part out, you'd use the cosine function. Because cosine is adjacent. So if you use cosine, that'll pull out the horizontal part. If you want to pull out the vertical part, opposite, hypotenuse, you use sine. Okay, so multiplying a value by the cosine gives you just the x part. Multiplying a value by the sine gives you just the y part. And what's this come from? Well, that's going to be given to you in the problem. That's going to be what your polar equation was, right? You're just multiplying by cosine and sine to pull out the horizontal and the vertical. Okay, we're gonna do one. Okay, so here's a parametric equation. I'm sorry, polar equation. R equals 7 sine 2 theta. Now, the x and the y are both jammed into that, right? Because all that this formula right here gives you, well, you tell me, what is it in that box that's equal to what letter?
Y.
What letter?
Y.
R, right? What's in that box is equal to R. So what that box gives you is this. I'm not going to draw the whole picture. I'm going to draw one single point. That's one point in that picture. Perfect. R is telling you this. It's giving you the distance from there to there. You want to break that distance into its horizontal and vertical components. So you really need this part and this part. Not this part. Not if you're going to change it to parametric. So what trig function do you always use to get the horizontal part. About me? What trig function do you use to get the horizontal?
Sine.
No. So on these formulas, x is the horizontal, cosine. Alright. So to get the horizontal part out of the radius, okay, the radius is a diagonal. I don't want to know the diagonal. I want to know the horizontal and the vertical. I'm going to use cosine. And now it's cosine of, we're writing parametric. So what letter should I use as the parameter in cosine? Yeah, Rob? Right? T. Yeah, T. So you're going to have to put a formula here and multiply it by the cosine. And that'll give you the horizontal part of the radius. You're going to have to put the same formula here, but what would you multiply it by to get the vertical part of the radius? Sine t. Cosine t gives you the horizontal part of your radius. Sine t gives you the vertical. Now, what goes right here? The function they gave you in the problem. Just make sure you change your theta to a t. So here's the function they gave me. So what would I put in that blank spot in front? Chris?
7t or 2t?
You lost some stuff.
Oh.
You need the whole formula.
7 sine 2t.
Yes. 7 sine 2t. That is the formula for the radius. When you multiply it by the cosine, you're just getting the horizontal. Right? Same thing here. That's the formula for the radius. But you don't want the whole radius. The radius is a diagonal. You want just the vertical. So multiply the diagonal by the trig function sine, and that always gives you the vertical. It's kind of like breaking a vector up into its components, the horizontal and the vertical. And that is your formula. So let's graph that. Let's see what's. I'll do it in polar first because I'm already in polar. Does anyone know what this one's going to look like? 7 sine 2 theta. It's kind of an interesting one. A little too complicated to spend a lot of time on by hand. Basically, it's going to look like 4 petals. And each petal, well, let me put the picture over here. How long do you think each petal is from there to there? Can you guess? Yeah?
7 sine 2 theta.
Just 7. Yeah, just 7. So the number in front tells you how long the petal is. This number controls how many petals you get. You can do all kinds of things. If you put in odd numbers and even numbers, there's different patterns. You can play with it and see what happens. But you get hundreds of petals. Okay. But that's what it is in polar. Now in parametric, now we got to, in our mind, think about breaking it into x, the horizontal and the vertical. So here's the formula, but you don't want the whole formula in x. All you want is the horizontal. So multiplying by cosine does that. Okay, it gives you like the bottom of the triangle. 7 sine 2t. That gives you the whole thing. That gives you the diagonal. You don't want the diagonal. You want the y value of the diagonal. So you use trig, and you multiply by the sine. If I hit graph, you get exactly the same picture. Notice it's drawing slower. I think it is. It's probably because the polar equation is more efficient for the calculator to do it than the parametric, because the parametric is 2 separate equations. But either way you do it, that's how you change polar to parametric. Okay? Just take your polar equation, put it in front, multiply it by cosine for the x. Take your polar equation, multiply it by sine to get the y. Okay? And of course, change your thetas to t's, because we don't use theta in parametric. Okay, so that's called a 4-petaled rows. That's the name our book gives it. The petals have a length of the absolute value of the number in front of the petal. And again, if you have time and you want to try it, try sine 3 theta. See what happens. 2 theta gave you 4 petals. Will 3 theta give you 6? No. Try it and see. And try it with evens and odds, because that's the pattern. It does one thing for even numbers in front of theta. It does one thing for odd numbers. You want to get really crazy, put a number like 2.4 theta. Then it gets really wacky looking. Right. Any question on that? Okay, let's look at this one. Last one. So this is a spiral. Okay? Specifically, it's called the spiral of Archimedes. So the other day after you guys left, when we talked about different kinds of like functions and weird things you can draw, I started looking stuff up and I found this like thing. There's like 50 or 100 things in this PDF I downloaded, and they're all named. Like the spiral of this guy, spiral of that guy, the curve of this person. There's like thousands of different things you can draw, but this one's pretty basic. So this one says that the radius equals the angle. So as your angle gets bigger and bigger and bigger, you're moving further and further away. That's the definition of a spiral. If your angle is 360, your radius is 360. If your angle gets smaller and it's 40 degrees, your radius is 40. So the bigger the angle, the bigger the radius. Okay. So let's graph these with just different intervals. If I graph, let me go back to polar. If I graph a spiral from 0 to 2 pi, how many revolutions of the spiral am I going to get? From 0 to 2 pi. Now, 1. Just 1. Now, I'm going to set it to 2 pi. You've got to set your theta step to a decent value. If you do it at 1, watch what happens. It doesn't really look good. You didn't plot enough points for it to make a nice smooth spiral. I would probably set it to like 0.1. That's pretty good. I can still see it's a little bit rough, but you can get the idea pretty good. Now, what's going to happen if I go to 4 pi? How's the picture going to change? Yeah, Chris?
It's going to be 2 revolutions of the spiral.
Yep, I'm going to get 2 revolutions of the spiral. So there's 1. I'm going to go off the screen probably. Yeah, I do. So there's 2. Now, what if I did 0 to 8 pi? What would I get in this case? Yeah. We're going to get 4 revolutions. I'm making my window negative 8 pi to 8 pi in every direction. That's a little overkill, because the only direction you really need 8 pi in is this part going this way. That's where it's going to be the biggest, okay, as you head to the right. Okay, let's take a look. So we got 1, 2, 3. I should be good. Okay, 4. And there's my spiral. Okay. So this just changes the amount of revolutions you see. Okay, let's try negative 8 pi to 0. So that's 8 pi to 0. See what happens when we go negative 8 pi to 0. Now, part of this might be something you would have had to watch as it was graphing. Maybe it's going to change the direction it spiraled. Maybe you'll be able to see it without just looking at the final pictures. But let's graph that. Well, that's different. Right? It didn't. This one started at the outside and it spiraled in. The other one started at the inside and spiraled out. Now, is it the same picture? Just kind of compare the two. Is it the same picture? Yeah.
It's flipped horizontally.
Yeah, there's a flip in there. It's a mirror image. So not only did it spiral the other way, it mirror imaged it. Right? And you can play with the spiral, and you can do all kinds of things. Maybe you can spiral it inside out, outside in, you can mirror image it. All kinds of things you can do with spirals. Good. Any question on that? So homework, this is the last homework assignment in the book. Tomorrow's homework is going to be in a packet. If you're not here, I have them. If you're going to be here, I'll just give you the packet tomorrow. Don't forget, this test is going to go on term 4. Tomorrow is your last homework assignment for term 3.